This is Team Wiz. Uh, this is our phase two work. I will be giving a short brief on our team consistency and workflow. So, uh, we met in the library for the discussion till nights and clarified each other doubts for a streamlined model training and understanding. So, what each member has done, I will give you a short brief. So, Udit handled the research backbone of the project, designing the trust scoring model, selecting verification parameters, and architecting the multi-stage cross verification pipeline. Whereas Divya led the EDA process and contributed significantly to data cleaning by rigorously testing the dataset uh, with her code, ensuring the accuracy and reliability of her final dataset. Whereas Rishik executed multiple algorithms and performed in depth analysis, working to optimize the model's accuracy to align closely with market standards. And I checked the workflow whether it is going in the right way or wrong way. Thank you.
We use the live data set. It had 12,000 plus political statements fact-checked by experts. We choose this because it has 20 features per statement. It's not just text, but speaker's history, party state, and add credibility scores too. We built three types of features. First one was text features, where we use TF IDF on statements, subject and context. We used unigrams, bigrams, and diagrams to capture word patterns and phrases that indicate deception. Another we used speaker metadata, targeting encoding for speakers, their historical truth rate, one hot encoding for party and state. Third, we used numeric features, credibility score counts, standardized using T-score normalization. Why combine all three? We combine all three because deception isn't just in the words, it's in who says it, their history, and the context. A Republican senator talking about healthcare in a debate has different credibility than the same senator discussing economics. We need to capture these feature interactions. So now moving towards model selection justification. We tested two models deliberately. First one was logistic regression, our baseline model. Simple linear model, it had us the accuracy of 73.4% with an F1 score of 0.73. This validated our feature engineering and was strong. Even a simple model performed this well. But logistic regression assumes features work independently. It can learn. The speaker lies about healthcare, but tells the truth about economics. That's a feature interaction. So that's why we used XGBoost as our primary model. It is a gradient boosted trees. Each tree learns from previous trees' mistakes, and trees naturally captures interactions. They can ask, is speaker X talking about topic Y in the context Z? So our XGBoost model made us achieve the accuracy of 74.9% with an F1 score of 0.742, with a flabbergasting improvement of 2.1%, representing capturing real interaction patterns from noise. So why not transformers like Bird or Robert A? They got 85 to 96% accuracy, but they need GPU infrastructures, and 10 key samples often goes over fitting for them. And they are black box basically. We can't explain their predictions. But we wanted to understand classical ML's limit first to go ahead with them. So for experimental rigor, we use 80-20 stratified split. Preserve the 56% true and 44% false distribution both train and test sets. Prevents bias. Since class-based and logistic regression made the model care equally both about the classes, not just predict majority class. So multimetric evaluation was accuracy was overall correct. Even score was balanced and was precise. Confusion metrics showed exactly where models succeeded and failed. So as per classic metrics ensures we are not biased towards one class. This prevents hiding behind inflated accuracy on imbalanced data. So why these choices? Why TF-IDF over word to big? So we chose IDF-IDF over word to big because it was interpretable. We can see which words matter deterministic, and are reproducible. So file logistic regression baseline. We chose it because it was fast, interpretable, and it tests feature quality independently of model complexity by XGBoost over random forest. Sequentially boosting correctness error batters the things. So it has a built-in regularization which prevents overfitting. And why we did not choose deep learning first? So we chose to start simple, understand deeply what works, and the complexity only if justified. That's proper research methodology. So, moving towards the conclusion, we achieved flabbergasting accuracy of 71.9%, beating classic ML baselines of around 60% on liar dataset, the methodological rigorous approach. Our contribution demonstrated that model feature engineering with really boosting captures political deception patterns effectively. We've established interpretable baselines that future research can build on. So our next steps are like testing transformer models, analyzing speaker-specific patterns, and validating on other datasets. So research isn't just about accuracy; it's about understanding why deception happens.
In my part of the project, I worked on preparing the data and building the first machine learning model. I started by importing the main libraries, pandas for the dataset, regex and NLTK for text and cleaning, and scikit-learn tools for vectorization and logistic regression. Then I loaded the LIAR dataset and assigned proper column names. Since the original dataset has 6 truth labels, I simplified them into just 2, true and false. The first 3 labels were grouped as true and the other 3 as false. Next, I cleaned the dataset. I wrote a pre-processing function that lowercases the text, removes punctuations, tokenizes it, removes stop words, and lemmatizes words. I applied this cleaning to the statement, subjects, and context columns so that the text becomes consistent and machine readable. After that, I converted the text into numerical features using TF-IDF uh, model. I used the statement column used high dimensional TF-IDF vectorizer with unigrams, bigrams, and trigrams, while subjects and context use smaller TF-IDF models. I also prepared numeric and categorical features. Numeric values were standardized, and categorical values like speaker and job were encoded. All these features were then combined into one final feature matrix. I included the binary labels, split the dataset into train and test sets, and finally trained my first model, logistic regression, with balanced class weights to handle label imbalance. And this is what the accuracy came out to be.
Why we used XGBoost while logistic regression was working well. Logistic regression gave us surprisingly good performance. It handled TF-ID of text features well and gave us around 73% of F1 score, which is above all classical ML baseline models. And however, logistic regression is a linear model, right? So it assumes that every feature contributes the output independently and linearly, but the dataset we use, which is liar, isn't linear at all. So logistic regression was not enough for the liar dataset. So and liar dataset mixes very different kinds of information such as text, topic, metadata, speaker credibility history, political party, state, and context. This relationship between these features is not linear. For example, a conversational topic plus a speaker with high false history and a different political party can combine in different logistical regression simply cannot capture those complex relationship between each feature. So we implemented XGBoost, which helps in this case where it understands complex interactions between these features and also picks patterns like certain speakers are only reliable on specific topics, some contexts like debates correlate differently with truthfulness, and also XGBoost compares state, party, speaker history and creates interaction patterns. These interactions are impossible for logistic regression but are natural for XGBoost. So we combined TF-IDF from statements, TF-IDF from subjects, and TF-IDF from context and numeric credibility scores, and also target encoded speaker data, one hot encoded state and parties, and scaled our numeric features. And the performance gap actually proved it. While logistic regressions F1 was around 0.73, XGBoost gave us around 74 to 75. But like yeah, the actual difference is only 1 to 2%. But actually, based on the liar dataset, 1 to 2% gain capturing the real interactions rather than random noise gave us a huge advantage over already available research currently happening. And now coming to how we implemented our XGBoost, here it is. We split the data into 80-20 training and test split, and which means 80% of the data is used for learning the patterns and 20 is kept hidden for final evaluation to check whether how well the model generalizes. And we for logistic regression we used balanced key weights to handle the dataset imbalance. For XGBoost, we tuned key parameters like number of trees, learning rate, and depth to ensure it learns non-linear patterns effectively. And after how we measured performance, coming to the performance, we used accuracy, macro F1 score, and classification report. And here is the confusion matrix to compare both the models. While macro F1 is important in our case because both classes are not equally represented. Yeah, and also we extracted the top TF idea features to see which words were most associated with true and false statements. And from XGBoost, we pulled feature importance to understand which parts of the dataset, like text, speaker history, or metadata, contributed most to predictions.